Okay, this is Mr. Spensei, your stats sensei, and I'm going to be running paired hypothesis tests and confidence intervals. This is going to be a little bit longer video this time. Hope you'll pay attention through the whole thing. But we're going to break down the recipes for the paired hypothesis test, and then we're going to run one. And then we're going to run a confidence interval over that same data. Well, first off, the nice thing about the paired test is it runs just like the one sample test that you've already done, or very, very similar. Because in a one sample, we had, we'd write our null hypothesis, and our null was expressed mu equals whatever. Well, here, it's going to be mu with a little d for the differences, because we're subtracting one from the other. So mu d, and for AP statistics, we can plan on this being a 0. I have yet to see them make a situation where it wasn't 0. And basically, by making it 0, we're saying there's no difference. There's no difference between whatever it is you're measuring. And the alternative would be mu d, and it could either be different, less than, or greater than, but still looking at 0. Now, I have to be honest with you. In this particular case, you may want to define your parameter first, but that's going to be up to you. The next thing you will need to do is write your conditions. So look at them. All right. So conditions are a random sample, and that will be given to you. The next thing, the differences are independent. This is a new condition we haven't had. And basically, it's just saying when you measure the difference of one thing, it shouldn't impact the differences of the other thing. And generally, that's going to be something that we have to assume. And we just need to give some sort of explanation as to why we can assume it. It can be very simple. The next thing, our sample size needs to be less than 10% of the population. And then the differences, they will either tell us that we have our normality, and we're going to refer to the differences. So in this case, the differences are normal, or n is greater than 30. Or if they give us data, we're going to have to create a box plot in order to show that. Well, when we're doing a one sample t, our formula was t equals x bar minus mu s divided by the square root of n. Well, our formula here is essentially the same thing, but we now drop some d's on it because we're saying we're working with the average distance from this average difference in the sample, the population mean difference, which really, because of our null hypothesis, is going to be 0. The standard deviation of the differences, and then, of course, our sample size. If we are given data, we're going to have to enter the data. And there's a couple ways to calculate our X bar. You can either do that through StatCalc 1-bar stats, or run the test, and usually I run the test, and then we can plug our values into the equation. All right? This is the way you run the test. All right? And as before, once we get our p-value, we write it down. And of course, if the p-value is less than alpha, we reject the null. If the p-value is greater than alpha, we fail to reject the null. Our template for our writing is our p-value is whatever it was we calculated here. Then we give our decision. We rejected the null. And we say there's sufficient evidence that alpha equal that was assigned to it to suggest a true population mean difference. All right, very important that you include that word for whatever it is we're testing. That was our parameter. Then we restate our alternative, much the same for our fail to reject. So let's go ahead and get into a problem. So in our problem, we have one indicator of physical fitness is resting pulse rate, and 14 men volunteered to test an exercise device. We're going to assume it was a random sample. We'll talk about that in a moment. Advertise on TV by using it 3 times a week for 20 minutes. The resting pulse rates in beats per minute were measured before the test began and then again after. So right here, this phrase right here indicates to me that since it's a before and after, because it's a before and after situation, we're looking at paired data. And sure enough, I have this person's name. I could have just put a number, but this person's name, and they were measured twice. This one was measured twice. And notice my data links are exactly the same. So it's like, hey, this is paired data. So we're controlling for the differences between the individuals. And then it says, is there evidence this kind of exercise can reduce resting pulse rate? So I'm going to skip my alternative, my null and alternative for a moment and talk about writing my parameter. So let mu d equal the true population mean difference in resting pulse rate or resting heart rate. And then I need to always tell every single time I need to say my order, which I chose to do before minus after. It really doesn't matter which order you choose, but you need to tell us what it is, otherwise you won't get full credit. So I'm going to choose a pulse rate, and let's just say my before pulse rate is 73, and then it said it needed to reduce, which means my after needs to be less. Well, in that case, 73 is greater than 70. I'm going to use that to write that inequality to establish my inequality for my difference. So the null hypothesis is mu d, or the differences are equal to 0. There is no difference after the exercise program. Or mu d, the difference is greater than 0, that the before was bigger than the after, that the pulse rate was reduced. So the conditions was random sample. Actually, I'll be honest with you, this was not a random sample. This is a list of my students. The first year I taught stats. But we're going to assume that these young men are representative of the population. Probably not a good assumption, but we have to assume that they're representative. Otherwise, we can't carry out the test. All right, the differences in pulse rates are independent. That is the new condition from the recipe. That's the first time you didn't see that on our previous test. Now, our previous recipe, but differences need to be independent, and that's the new one. Now, about that I want to say is it is actually reasonable to assume that, because truthfully, his difference, his before and after, should not impact Tripp's before and after, should not impact Matt's before and after. So it really is reasonable to say that they're independent. Now, in this case, what was my sample size? Well, I have 14 men, and sure enough, I count across. Now I see I have 28 measurements, but that's because the 14 men were measured twice. So I can either do 14 divided by 10 or 14 times 10. And there are more than 140 men in the population. So my sample size is less than 10%. And I really need to add that to it. The sample size is less than 10%. Size is less than 10% of the population. All right. Now, the next thing, we need to check normality, and we're going to do that by creating a box plot. Before minus after, putting a label for resting pulse rates. All right, so how am I going to do that? Well, earlier I went to stat edit and I entered the first row into L1 and the second row into L2. Now, what I really need to do is I need to subtract all of these because we're looking for differences. So really, I should be going, okay, this is 0, this is 2, this is 4, et cetera, but I can get the calculator to do that for me very easily. It's kind of nice. All right, I'll go up to the top of L3, so L3 needs to be highlighted, and I'm going to press second 1 minus second 2, and there I get all the differences in that column. Now I need to go create the box plot. Make sure go to y equals, make sure that's cleared out, and we're going to go to the second stat plot. The only stat plot that should be on is number 1. If 2 and 3 are on, please turn them off and can create problems for you. So I'm going to press enter at this point, arrow to the left to make sure it's on. Then I'm going to drop down and I'm going to arrow to the right until I get to the box plot showing outliers. All right, and we really don't want any outliers. Now, my before is an L1, my after is an L2, but the differences is what I'm looking for is an L3. So second 3 and press enter. And then at this point, I'm going to press zoom 9. So zoom followed by the number 9. And there I get my box plot, and I can use the little trace feature right here to get my values as I go across, and that gives me my major values for the box plot. Well, I see it's not really even exactly, but this distance and this distance are about equal. So there's about 50% here, and there's 50% here, and it's about the same distance. So it's not excessively skewed, and there are no outliers. It's okay to say it's approximately normal, or it's okay to use the normal. All right, so I need to go ahead and at this point, once I have my box plot, I should be writing down my equation, which is T equals X bar D minus mu D. And then it's the standard deviation of the differences divided by the square root of n. Well, there's a couple different ways to get that information. Now, I'm going to show you 2 different ways. We can go back, just because I didn't want you to forget about this. We can go to press the stat button, arrow over to calc, 1 variable statistics, and the list of data we're interested in is an L3, so second 3. And there's my X bar, there's my standard deviation, and there's my 14. That's one way to do it, and there's nothing wrong with that, but I tend to just be a little bit hurried, and I'll go stat test, and I'll actually run my t-test at this point. There's my t-test. Now, we are not working with summary statistics, we're actually working with the data. Since we have data, now what was the mean that we were looking for? Where our hypothesis mean was given as 0, so I need to make this a 0. My data that I'm interested in, the before was an L1, the after was an L2, but the difference is what we care about is an L3. And I notice that I have a greater than for my inequality, so I need to make sure that I have a greater than on the calculator. And I'm going to press calculate. And I get the t-statistic, a p-value, and x bar, and the standard deviation of x. Well, right now, I just need the x bar and the standard deviation of x, and I go ahead and plug them in. So I have the probability that t is greater than my x bar of 2.57 divided by my standard deviation, which happens to be 2.24, divided by the square root of 14, and that equals the t-value of 4.289 and gives us a p-value of 0.004. I want to draw a picture of what's actually going on here. So what's actually going on is we have a claimed mean that there is no difference. There's no difference between before and after resting pulse rate. And so our claimed mean is that our mu is 0. Well, when we actually ran the test, we ended up getting a difference. We ended up getting a difference of 2.57. And we had a greater than, so we're shading this way. And this was my X bar. So these are my actual values. But then when I run a t-distribution, the t-distribution is centered on 0. And we ended up getting a t-statistic of 4.289. So this 0 matches here, and this matches here. And these are my t-values. And the probability, or the amount of shaded area in this case, happens to be 0.004. That 0.004 represents the probability of getting a value this extreme or more extreme, given that there really was no difference. Well, my p-value is 0.004. They didn't give me an alpha, so we're going to use the 0.05. And obviously 4 is less than 500. So consequently, our decision is to reject, because remember, if the p-value is less than alpha, we reject. So our p-value is 0.004. We reject the null. There is sufficient evidence at our alpha level of 0.05 to suggest that the true population mean difference in resting heart rate How did we subtract? Before minus after is greater than 0. Please notice we added, instead of just the mean, it's now the mean difference. So this is a new word. And then we need to make sure that we include the direction. All right, so this takes care of the scenario 1 hypothesis test. We're going to look at the confidence interval. It should go much faster, but we're going to do that here in just about 2 minutes. So with the confidence interval, we have the same conditions, the same parameter. The only thing that we really need to look at is we changed our formula, okay? Because our original formula, when we had a 1 sample, was x bar plus or minus t star s divided by the square root of n. All right, and if you're using the notes, you know that you can find all the information you need to run this test. Please remember, your t star directions can be found here, but it's the same as when we do a 1 sample t. So let's go ahead and get onto that. Well, when we go back to it, it's like, hey, you know what? We just already did this problem. So consequently, I'm not going to rewrite these and go through all of these conditions because it's exactly the same problem. So we're good all the way through. We've done our parameter. We've done our conditions like we're supposed to. Nothing's changed there. So how do I go about getting this information? Well, I've written my formula. I go, all right, x bar d plus or minus t star, the standard deviation of the differences divided by the square root of n. Well, once again, I can do that through StatCalc 1 var stats, or I can just go ahead and run the test, which would be stats test, t-test, t interval, because we're doing it, which is number 8. Data needs to be highlighted, and our list is in L3 because we care about the differences. So make sure second 3. And they asked us to run a 95% confidence interval. So this needs to say 0.95. And we're going to go ahead and calculate. At this point, I'm going to get a lot of information. I have my X bar, my standard deviation of the sample, and this is my lower bound and my upper bound. So I have 2.57 as my X bar. I also have 2.24 and I have 14. What I don't have is my T star value. I don't know where this came from yet. I haven't calculated that. So let's go back and calculate our T star. And by the way, here's our lower bound and here's our upper bound. So I'm going to go stat. So to get my T star, I'm going to go second vars, inverse T. My area is going to be parenthesis 1 minus 0.95, close parenthesis, divided by 2. And my degrees of freedom, well, we had 14 differences, so 14 minus 1, because it's n minus 1. And that's where my 2.16 is, and I choose to make it positive because I'm a positive person. All right, so we end up getting these differences in a lower and an upper, and what that means is, in this case, is our data, or our confidence interval, which this area right here is 0.95. We have 0.025 in this tail and 0.025 in this tail. And this marks my lower bound, and this marks my upper bound. And my X bar is always in the center. And my X bar happens to be 2.57. And then my lower bound was the 1.27. And my upper bound is 3.86. And what I know about this is I know I am 95% confident the true population mean lies somewhere between here, between the lower bound and the upper bound. Which means in this case that there is a difference, and I'll explain that in a moment. So we are 95% confident the true population mean difference in resting heart rate before minus after lies within this interval. Please note that any value in the interval is plausible. So 1.278 is plausible, 3.867 is plausible. Anything in there is plausible. 4 is not plausible, and 0 is not plausible. If we're explaining the confidence level, we'll say in repeated sampling, we expect that our method is so good that we'll capture the true population mean difference. By the way, I should have made this notation because we have mean difference, and that difference is a new word that we're adding for this test. And we all need to include our direction 95% of the time. One thing we'll note is that 0 does not lie in the interval. Therefore, we are 95% confident that there is a difference in resting heart rate. All right. If 0 had been anywhere in the interval, even if it's barely inside, then we couldn't make that claim. But here we can say, you know what? Based on this, there appears to be a difference in before minus after. All right. Thank you for watching. Hope you'll catch the next scenario.